we have been discussing superconductivity, and we will soon end this discussion. What we want to show you is something extremely important, that there is a famous work by Andreev, which predicted even before any experimental evidence that there should be a state where magnetic flux should penetrate a superconductor for certain kinds of superconductor, and in that case the flux will penetrate in flux tubes with quantized vortices, and the the amount of flux will be like Dirac flux, quantum of flux for 2e charges. Now we know that its charge is 2e, and at that time it was a revolutionary suggestion, because there was no experimental evidence for it, and it just came out of a calculation that he did using Ginsberg Landau theory. See, Ginsberg Landau theory was already there in 1950, and it phenomenologically explained many things that happen inside a superconductor, or for that matter in across any phase transition, and that is what we want to discuss. But just to recap, that we discussed tunneling also. We found that tunneling is an extremely good experiment to measure the gap, because this I versus V characteristic from a normal to superconductor tunneling gives the gap, measure of the gap at low temperatures, and the differential conductance gives a direct probe, acts as a direct probe to the density of states of a superconductor, and that is, as you can see here, there is this features of a pile up of density of states right after the gap, and then there is this tailing off, and that was obtained by tunneling measurement. So, tunneling has come to be an extremely important measurement technique for superconducting density of states, the nature of the gap, and if the gap, if there is a full gap or there is a pseudo gap, and all kinds of things can be obtained from tunneling measurements. Okay. Then we discuss something extraordinary, which is that there is this famous tunneling situation, which is called the Andreev reflection, in which an electron from a metal is injected into the superconductor, and then in that case, apart from the specular reflection that can happen at any boundary, there was this remarkable phenomenon that instead of the electron coming back, a hole comes back, and not only does it come back, it just retraces the path of the original electron backwards. So, this was actually it cannot happen unless there is a superconductor on the other side. So, this is for example, gaps are there in semiconductors. So, I can think of normal to semiconductor tunneling, but we cannot get this Andreev reflection, for example, at a normal to semiconductor junction. So, anything which does not produce these Cooper pairs on the right hand side will not produce this Andreev reflection. So, that is actually a telltale signature that indeed Cooper pairs are produced. There are two particle bound states on the right hand side, particles pair up, and this hole then has to come back on the left hand side, and just from conservation rules, it has to retrace the path of the original electron backwards. So, that was a remarkable experiment we discussed, and then we discussed how to project out the n particle states or n by 2 pair state there are n particles, that means n by 2 pairs out of the BCS ground state. Look at the BCS ground state, it has enormous fluctuations as it is not a number eigenstate. Although the fractional fraction delta n RMS by n is still very low, and that is why you can do a theory of superconductivity in a macroscopic system without conserving the number, you can work on it. But still the fact that you should be able to show that there is a way to get the finite number wave function, and that is from here one just goes one more step and integrates out all the phase, and then when n by 2 is equal to this see these vk's contain the phase. So, suppose there are n by 2 number of vk's in this wave function, and when and that particular one will be picked up by this n by 2, because there will be a delta function, right. So, so n by 2 minus say alpha times phi, if alpha is not equal to n by 2, then this will be 0. So, only the alpha equal to n by 2 term will be picked up from this product, and that means that you have taken alpha times Vk. So, twice alpha number of electrons. So, that is the way to pick out a finite number eigenstate from this, and then that is another corroboration that there is this uncertainty that delta n delta phi must be greater than 1, and that is borne out by this calculation, this famous very intuitive, very nice and very simple calculation. And this also predicted the way forward towards something called Josephson junction, which has come to be known as Josephson junction, and it just shows that if there are two superconductors, the same superconductor, for example, take niobium for example, two niobium superconductors are joined together and maybe with an insulating, very thin insulating barrier, then these two superconductors are identical. They would like to become one superconductor, and then the phases must be equated. The phases must become equal, and in order to change phase, you have to change the number. That means electrons or pairs have to flow from one side to the other. That means there is a current, but without any field, without any potential. So, that is actually what is this famous Josephson current is, and that happens only if you have superconductors, where the good quantum number is the phase and not the number. Numbers can fluctuate. Once you try to fix the phase, numbers become uncertain, and that is the ramification of that is this flow of current without a voltage. We will come to that towards the end. So, let me just now go ahead and write down the Ginsberg Landau theory, which I had introduced the other day, and the idea is that you have to write the free energy in a way that the free energy as a function of some order parameter, say n m, and that is what is done here. And then what we showed was that from this kind of a free energy with say free energy as a function of so free f. So, let me put the normal state free energy equal to 0, this I set to 0, and so this free energy is an expansion close to Tc about the normal state free energy. So, we can write it as a by 2 m square plus b by 4 m to the power 4. This by a by 2 and b by 4 are chosen in such a way that when you take the derivatives, this 2 will cancel with this 2, the 4 will cancel with this 4. That is about it. There is nothing, no mystery about it. So, this is the situation when a is greater than 0. Remember, b is always greater than 0, otherwise you cannot have you will have an m going to infinity solution. So, the situation changes when a becomes less than 0 and that is what we showed, that this will become m naught and m naught square equal to minus alpha by b beta minus a by b, sorry. And a being negative, this is perfectly all right, this is positive. So, you can actually put it back in, and then the f minus fn is set to 0. So, let me just again not use fn, and then f equal to in the ordered phase where you have a finite m naught is the solution. See, this I obtained by taking a derivative of del f del m equal to 0. The solution of that is this, and then I put that solution back there. So, a by 2 into minus a by b plus b by 4 into a square by b square. Okay. So, this is minus a square by 2b plus a square by 4b. So, it is minus a square by 4b. Okay. So, this gives me m a m plus b m q. So, that solution is m square equal to minus a by b. So, this is the free energy. So, that is the value. So, that is our minus a square by 4b. So, that is a stabilization that comes, it is a negative energy, and that means that your energy has come down below the original m equal to 0 state, which is at 0 energy here. At m equal to 0, it is 0. So, that is how Ginsberg Landau free energy is done. So, let me just tell you a bit more formally what is done for superconductors. For superconductors, same thing is done, but the choice of order parameter, which is non-zero below the T c and 0 above the T c, is a bit it requires a bit of intuition, and that is what these people did. One could, for example, choose a gap. Gap is non-zero below T c and 0 above T c, but gap is not the right quantity to choose. You can show, of course, later on Gorkov had shown that this psi that is chosen here has some relation with the gap, but let us not get into that detail. Let us just follow what Ginsberg and Landau did, and so what they did was that they chose a kind of a pseudo wave function psi, and in terms of that they wanted to write down the free energy. Psi is in general complex. So, it has it is some psi e to the power I phi. Okay. So, it has both magnitude and phase. Now, three things one should note is that the free energy is a real quantity. So, you cannot expand in terms of psi. So, free f is real. So, can't use just psi, right. So, this is kind of a polynomial expansion we are doing around the free energy of the normal state at, and this is so valid very close to T c, because otherwise psi will be large and you cannot do that. So, mod psi has to be small in that region, this is valid. So, and then problem is that psi cannot be used because it is a complex quantity. Then one could think of psi real part of psi. Well, that also cannot be used, because then that will depend on the phase, absolute phase of the wave function, and the free energy should not depend on the phase of the wave function of this wave function psi. I mean, the free energy should not depend on the choice of your phase. And 3 is can we choose mod psi? Sorry, mod psi. the problem with mod psi is that every odd power of mod psi is non-analytic at psi equal to 0. So, mod psi, but this is non-analytic at psi equal to 0. So, that you cannot choose because free energy is after all a analytical function. You have to take derivatives and all that. So, then the natural choice that is left for them was take mod psi square. So, this is the order parameter they chose, and that is how the whole thing is done. So, that is an expansion using mod psi square. Okay. So, once one does this, this algebra you can if you like you can repeat, it is not difficult at all. Those who have done classical mechanics have used this, classical field theory have used this, but even if you do not want to do the algebra, it is worked out at places, you can try to take a look at it. It is absolutely straightforward, it is not difficult at all. The notation, these complications come from this term, the canonical momentum. Anyway, so once so the minimization has to be done with respect to mod psi, with respect to psi and psi star, and you can so minimize f, you have to minimize with respect to psi and psi star, and you can get this equation. The h square by 8 pi is added because there is a magnetic field, because there is A sitting here, curl A is h. So, that has to be incorporated there because the magnetic field has its energy density, right, which is h square by 8 pi. So, okay. So, the equation of motions there are two, there is another one through here, another variable which is A, the vector potential. You have to extremize the free energy with respect to A as well. Okay. Okay. So, then you get these two equations. This is the first one, this from minimization with respect to psi star, and this one is by minimizing with respect to A. Remember, H also contains A through curl of A. So, that has to be that has to be realized. So, and this is of course that gives the Maxwell equation that will so that J normally del f del A is equal to J, the minimal coupling is J dot A. So, it gives you J. So, that is so that gives me this J, which is equal to C by 4 pi curl of H from Maxwell equation, and that is equal to this. Okay. So, this is done then, and so minus sign. The next step is this, that you can write psi as mod psi e to the power I phi, and assume that mod psi is a much weaker variable in terms of r. So, mod psi does not vary too strongly with respect to r. See, all these terms, the gradient term that has been taken here is because the superconductor now is inhomogeneous. So, there may be regions which are superconducting, strongly superconducting, then maybe regions which are not so strongly superconducting. So, it has an R dependence. Earlier when we were doing BCS theory, superconductivity was uniform. Here of course, it is an inhomogeneous situation. So, for that it is, you cannot do BCS theory, and this is probably the best shot that one can do, and this grad term takes care of this inhomogeneity. And there is, so basically a change in psi costs energy, and that you take care of that by this gradient term. So, both psi and grad psi I mean having those costs energy, and then that energy is actually psi stabilizes and grad psi increases energy. So, we have to be careful, and we have, that is why all these terms are taken care in the free energy, they are kept in the free energy. Anyway, so I get these two equations, these two are my equations of motion, and then I can just sorry, this and these are my equation of motion, and writing psi r as mod psi r e to the power I phi I, I can just convert this to a gradient with respect to phi, the phase, assuming that the mod part, the amplitude part varies very slowly. And that is basically this equation that gives me the square times. So, if mod psi square can be identified, for example, I mean that is what in the back of their mind, because it is a kind of a wave function they thought, and this should be then connected to n sub s, the superfluid superconductor fraction, superconducting fraction. So, and then of course, then you can see that this equation is what you expect from simple quantum mechanical arguments. Okay. The boundary condition they used was this, that there is no current passes through the surface. Okay. Now, let us just try to solve this equation, and first thing is that we define a variable which is f equal to psi by psi infinity. By psi infinity, one means that the value deep inside the superconducting region. So, it is in the bulk value way far away from the surfaces, or defects or impurities, or if there are magnetic fields around inside, which we will come back to. So, all that is no disturbance, undisturbed bulk value of superconducting wave function. So, this is the so psi may vary within in a certain region. In an inhomogeneous superconductor, for example, it will vary, and that is what we are after. So, we will see how this quantity f behaves from these equations, and that will tell us how psi goes to its bulk value, which is the psi infinity. So, then one can just from this first equation, from this equation, if you have a equal to 0, then you can just write this equation in one dimension. For example, suppose you have a semi infinite superconducting, this side is superconductor, and then you can just the only variation is along the x direction, because this side is non superconducting, this is superconducting starting at x equal to 0 say, and then all that varies is along x equal to 0, y and z are perfectly symmetric. So, you only look at the x variation and write down this equation. Then look at this equation, there is this h cross square by twice m star mod alpha d2f dx2 plus f minus f cube equal to 0. This is what you will get. I mean, this is absolutely simple algebra. You just substitute this, divide the things by psi infinity, every psi divide by psi infinity, and you will get this equation from the previous one, from the equation of motion. Okay. So, what does it give me? It gives me this h cross square by twice m star alpha times this. Now, f is dimensionless because it is a ratio of two psis. So, the only dimension comes from x. That means, this h cross square by 2 m star alpha should also have a dimension of length square, just to cancel out this x. So, that means you can define a length scale psi square, which is of course a function of t. As I said the other day, that the coefficient alpha is generally chosen at t minus t c, so that it is positive above t c and negative below t c, as I just showed in the first discussion, the a coefficient, which is the alpha coefficient here. So, psi square t is h cross square by twice m star alpha. So, alpha is a function of t explicitly put in here. And then of course, as I showed, that alpha should be proportional to t minus t c, which is 1 minus t c by t, which is 1 minus small t. Small t is t by t c. So, that is put in here. So, psi square is proportional to 1 by t minus t c. that means psi is proportional to t. So, psi goes as t minus T c to the power minus half. Okay. Now, there is one thing you must have noticed that in this discussion we are using this E star and M star, and that is what is generally used, because at that time no one knew what is the charge of these objects that we are dealing with and what is the mass of these objects we are dealing with. And now we know, of course, these are 2E and 2M. So, that is what M star finally one puts in to connect to experiments, but generally you can keep E star and M star. Okay. So, this is the equation has now become this, that psi square d2f dx2 plus f minus fq equal to 0. So, this is the equation that we will start now and work through it and show that how this equation gives me the psi deviating from psi infinity, and how that deviation behaves with as you go inside a superconductor.